Hey, Science 10. Let's talk about gravitational potential energy. We're going to be looking at that weight right there. Now, right now, if it fell, it would have a lot of gravitational potential energy. Let's take a look at that. Okay, if the weight fell from, only a few centimeters off the ground, it's not going to have much gravitational potential energy. We know that. It's not going to hurt much. Let's drop it. Okay, luckily the shoe is empty. But imagine if that weight was way up there and it fell down onto this poor shoe, and this poor shoe is of course on the ground. That would be a lot of gravitational potential energy. So your gravitational potential energy depends on the mass of your object, but not only that, how far off the ground the object has been lifted. The higher it goes, the more and more gravitational potential energy it has in it. Really, it's those two factors. Of course, remember, gravity is also acceleration. That's why it hurts. The higher it goes up, or the more gravitational potential energy. I'm not going to drop this on my toe from any distance, but if it was only a few centimeters off the ground, that wouldn't be very much. But if we put it way up here, and I can't even reach that, if it was way up there, it would have even more gravitational potential energy because it would have farther to fall. And the further it falls, the faster it's going to get going, and of course it's going to have more kinetic energy. Okay, let's look at gravitational potential energy. Okay, Science 10. So we've just seen a bit of an introduction to gravitational potential energy. Ultimately, it's stuff that makes sense. This individual here, they had to climb up this cliff, so that took energy, right? And now as they jump off, depending on how high they're going to go, or depending on how high they are, plus their mass, or multiplied by their mass, is going to predict how much gravitational potential energy they have as they fall down. Of course, it's going to be released as kinetic energy as they start falling. Gravitational potential energy is indeed because gravity accelerates objects at a known rate, and that acceleration is 9.81 meters per second squared. And all that means is with every second, we get faster and faster by exactly 9.81 meters per second. We'll take a look at that. Let me share my slides, and yeah, let's get underway. Have your calculator, have your physics formula sheet, and have your notebook handy. And yeah, let's learn about gravitational potential energy. All right, so yeah, gravitational potential energy. So, in our example that we started out with here, we've got this mass, and it's lifted off the ground. Now, we really even wouldn't want that to fall on our toe, but let's say it did. That would hurt a lot. But if we take the same mass and move it to the top of the ladder, again, it's higher off the ground, same mass. If that falls, that's going to really hurt the toe here. That's why we've got the shoe off, so we're good and safe. And that's ultimately what you want to be able to take away from this. Really, is that understanding that gravitational potential energy is to do with the mass of the object, the gravity on Earth, and then how high it's been lifted off of the Earth, or the Earth. Yes, the Earth. That is the place we're living on. Okay, let's take some notes about gravitational potential energy. And yeah, write it along with me here. And you can always hit pause as I'm going through stuff. So, the symbol we use, Eg, or energy of gravity, is equal to, well, here's some of the key factors, right? So we need mass. We need to know the mass. And then multiplied by the acceleration, due to gravity. And of course, on Earth, that would be different on the moon. And really, this is just saying we understand that the higher that we're up, if we jump off a really high cliff, we're going to be going pretty fast as we hit the ground, versus if we just jump off a set of stairs, it's just a small, tiny set of stairs. We're not very high off the ground. So acceleration due to gravity. And then, of course, like I was just saying, that change in height. How high are we? Now, of course, your mass is in kilograms. Your acceleration due to gravity is in meters per second squared. Again, it's an acceleration, getting faster and faster and faster, and depends on how high you are, your change in height, and of course, meters, listed in meters. Now, a reminder what energy is, this is of course measured in joules, right? And energy is the ability to do work. Right from the beginning of physics, we talked about that. Work is measured in joules. Work is energy, energy is work, and of course, yeah, energy is measured in joules. And that's what we're going to be solving for. Well, any one of these three variables. You might have a question that asks you, what is the gravitational potential energy? We could have a question that asks, calculate the mass, or we could have a question that asks, calculate the change in height. But yeah, let's take a look. Let's go to the factors. Let's take a few notes on those. We were just talking about it, but factors that give gravitational potential energy. All right, first of all, and it's right in the formula, the mass. And it's that weight or that mass that I was lifting off the ground above my toe on the ladder. If it was very, very massive, it wouldn't even matter if it's only a few centimeters. That would really, really hurt. Always measured in kilograms. Second factor, G, or gravity, right? Or acceleration, because that is what gravity is. And you really want to start thinking of gravity as that, as acceleration. That is what gravity is. Gravity is acceleration. Acceleration due to gravity is a very specific number. You're going to want it memorized. It's also on your formula sheet, but you're going to want to memorize this. 9.81 meters per second squared. Again, an acceleration gets faster and faster and faster every second, and that's the exact rate that it gets faster and faster and faster. The third thing to figure out gravitational potential energy is your change in height. Okay, and of course, delta means change. That little triangle there, change in height and in meters is our unit. And yeah, do yourself a little bit of a model. So let's have a very, very bad ladder here. And, depending on how high, it looks like a Christmas tree actually, but okay. Depending on how high, maybe we've got 0.5 of a kg. And depending how high we lift it off the ground, if we only lift it 0.75 meters, it'll still have some gravitational potential energy versus if we lift it 2.25 meters right to the top of the ladder, it'll have more gravitational potential energy. It's still the same mass, right? It's still the same acceleration due to gravity. It's all about the change in the height in this example. Let's take a quick look here. If you had to figure out, just looking at the picture, which has more gravitational potential energy, this right here on the left or this on the right. That's the exact same mass, but it's just a different height off the ground. Well, put your toe underneath one of these and you'll right away sort of know that, yeah, indeed, this here, the picture on the right, has a lot more gravitational potential energy. But yeah, let's make sure we're really clear on what gravity is. Let's take a look at that. Flip the slide. Okay, again, gravity is acceleration. So let's write that out. We're mentioning that, but yeah, let's write that down. Try to write a little neater than I do. On Earth, because that acceleration is due to the mass of the Earth, on Earth, acceleration due to gravity. And I think you've got it memorized by now, but write it out. 9.81 meters per second squared. Now in our example here, let's say we have a radar gun, right? And to measure speed, and we're not sure of how high this drop is. I mean, we can kind of estimate it obviously by looking at it, but we're going to use that radar gun. And what we know for sure is it takes 1 second, right? So maybe he's been jumping a bunch of times, and it takes exactly 1 second. Essentially, he jumps up. So basically, right from there down, that takes a second. Okay. The speed right there, just before hitting the water, right, is going to be 9.81 meters per second. Okay. Now, that's only a second. So we're going to need a little bigger cliff. Okay. So we got this cliff here. This person is being perfectly safe. Okay. They're tethered. Okay. So it's all nice and safe. And they're not going to jump. They're just going to drop a little rock. Okay. And there's nobody at the bottom. And it's also cleared. They cleared the bottom. It's all safe. And it's a big, tall cliff. Okay. So it's a long, long way. So we're going to get this bigger cliff. This person's going to drop a small rock. Again, we can measure speed, and we know exactly how much time is going by. So make this chart with me here, and just got to get my marker going. There we go. Okay, making the chart with me. So time in seconds, that's our unit for time, always in physics. And our speed, and that's always meters per second. That's what that line literally means. Divided by is another way of saying per. I'll just draw another line there. So at time 0, okay, we haven't dropped the rock yet, so it's got no speed. Okay, so we drop the rock again, perfectly safe. We're all tethered here. So after 1 second, 9.81 meters per second. Actually, I don't need to put those units there. I've got it up above, 9.81. Okay, so after 2 seconds, okay, how much faster? Well, it's meters per second squared. And what you need to know what that means is we're getting faster and faster and faster, and by a known rate. Okay, so you add 9.81 to 9.81, do it on your calculator, double check this, but it's going to come out to 19.62, okay, meters per second at that point. Okay, 3 seconds goes by, and again, we're measuring this. We've got a radar gun, okay, and we know exactly 3 seconds would go by, and then, hey, what's the speed right now at 3 seconds, right now? Okay, add another 9.81 to 19.62, you get 29.43, again, meters per second. Okay, the rock is still falling, and there's no effects from wind and stuff and air resistance, so it's falling perfectly, accelerating due to gravity, and that's what gravity is, it's acceleration. So at 4 seconds, again, at exactly 4 seconds, check the radar gun, and of course it reads off the speed in meters per second, and what we get is 39.24 meters per second. So you can see with each second we increase in speed, the speed increases exactly 9.81, and that's what acceleration is. With each second we get faster and faster and faster, and by a known rate, and that's exactly what gravity is. Gravity is acceleration. Now, what we maybe are wondering is, well, how far, right? How far does that little rock actually get? So let's add that to our little chart here. So basically just go a little further, and we'll go distance, and distance, of course, in meters. And of course, at time 0, it's gone nowhere. Now, I'm going to give you these numbers, and then I'm going to show you how this is actually calculated. So at 1 second, it's only going to be 4.9 meters. And you're going to think, really? But think about it. When we first drop that rock, or if you've dived off a diving board, at the beginning you fall pretty slow, but then you get faster and faster and faster. But right in that first second, you're not really going too fast, right? So it only gets 4.9, actually not 90, sorry, 4.90 meters. At the second, now we've already gone 19.62, so we're going further and further. At the third second, again, we go further and further each second because we're going faster and faster. we will have gone 44.145 meters. There's a way that we can calculate this, but I want you to write it down, and I want you to see these numbers. After the 4th second, it will have gone 78.48 meters. And think about that's a fair distance between the 3rd second and the 4th second. Of course, it makes sense. It's going pretty fast, right? By the end of the 4th second, it's now going, almost 40 meters per second. So it does kind of make sense that it travels a good distance, again, as it's constantly accelerating. Again, there is a formula for figuring this out, and what I want to show you is that formula. Okay, so, and write this down again in your notes. Formula for distance if you have a known acceleration. Okay, and of course we know what gravity is. Gravity is acceleration, and we know the acceleration, 9.81 meters per second squared. So formula for distance with a known acceleration. All right, now so that formula is, and yeah, write this down, and also you're going to want to get it on your formula sheet in case you need it. Distance in meters, obviously, equals 1/2, well that's cool, times g, or gravity, times the acceleration, because we could also use this formula if you had a known acceleration of a car or something, or a cheetah or whatever, but in this case it's just the acceleration due to gravity, so that'll be 9.81 obviously, and then times time in seconds squared. Now let's plug in some of the numbers here, and actually if you press pause and try this formula on your own, you're going to get these answers right here, but let's do them together, and let's do the 1st second. Okay, so after 1 second, d, the distance is going to equal 1/2 times gravity, 9.81 meters per second. Always put your units and always say your units, times 1 second, and of course squared. Now 1 squared is 1 times 1, right? So that's 1. So that's kind of boring. Ultimately, this is going to equal, let's put it beside here. Yeah, we'll put it right here. If you type it into your calculator, 4.90, and of course put your units meters. All right, so that's 1 second. Let's do 2 seconds. Again, write this out with me, and feel free to press pause and use this formula to figure out how far of distance in 2 seconds. But yeah, I'm going to do it right now. 1/2 times g times acceleration due to gravity, meters per second squared. Again, yeah, put your proper units there, Phil. Times 2 seconds squared, so 2 squared. Okay, and on your calculator, the way I would type it in, I'd go 0.5 times 9.81 times 2 times 2, right? That's just how I would do it. I mean, you could do the exponent first, right? 2 squared, and then 2 squared times 9.81 times 0.5. That'll work too, but just because squared is just number times itself, that's how I would do it. This, and you're going to get after 2 seconds the number we have up there, but yeah, we're checking if our numbers are correct. 19.62 meters. Okay, do 3 seconds. We've got it up there, but see if we're right? Use the formula 1/2 times 9.81 times 3 squared, or times 3 times 3. 1/2 times 9.81 meters per second squared. That's my acceleration, times 3 squared. 3 times 3 is 9, right? So again, 0.5 times 9.81 times 3 times 3. Remember, it's squared. It's not 3 times 2, right? It's 3 squared. And this is going to come out to 44.145 meters. Let's do the last one that we've got here. 1/2 times 9.81 meters per second squared times 4 squared. 4 times 4, that's 16, right? So 16 times 9.81 times half. When it's multiplication, it doesn't matter what order you do these in, right? And check them a couple times. and check these. Make sure I've done them right. Like, don't just assume, oh, it must be correct. Have your calculator, check this right now. And you will find out this is 78.48 meters. All right. I've got a graph here that I actually did in Excel, because in Excel you can put formulas in Excel and then you can make a graph. So I want to show you this in Excel. This is kind of cool. You've got these in your notes, but take a look at this right here. So that's this formula for figuring out distance, as long as we know the time and as long as we know the acceleration. And again, we're just dropping a rock off a cliff. Okay, so let me pop into Excel here. There we go. All right. So again, we're all nicely tethered to the cliff, being safe, and then we drop the rock. No one's on below. It's a small rock anyway. Time 0, no speed, no distance, and I've actually divided it into like 1/10 of a second. So you can see at 1 second, there's my speed, the 9.81, right? And then at 2 seconds, 19.62, and then at three seconds, 29.43, and then at 4 seconds, 39.24. Again, this is an increase of 9.81 each time. So you add 9.81 to 9.81 and keep adding 9.81. Again, just try that on your calculator. Type it in, 9.81 plus 9.81 plus 9.81 to figure out how much per second. So that's our speed. Here's our distance. Oh, there's our 4.9, right? And you can kind of see it here down on the side here. We've got our on our on our y-axis. We've got our distance. On our x, we've got our time. So this is time in seconds, and this is distance. And notice how it hooks up, right? An acceleration, a graph showing you acceleration hooks up because it's getting faster and faster. It's not a straight line. Straight line would be constant velocity. And there's no way if we jump off a cliff that we've got a constant velocity, right? So I wanted to show you this, just kind of how really cool this looks. And indeed, you know, you get, at first, we barely go any distance. Like to get a meter, it takes half a second. But then by a second, we've gone 4 meters. By 2 seconds, we've gone 20, almost 20 meters. But by 3 seconds, we've gone like 44 meters. That's a fair distance. By 4 seconds, 78. I'll keep going. This is kind of cool. By 5 seconds, 122 meters. Okay, this have to be a big cliff, and it's just a small rock falling, so don't worry. After 6 seconds, 176 meters. At that point, at 6 seconds, if it's a little rock or whatever, it's going to be going 58.86 meters per second in terms of its speed. So again, we've got speed here on the left and our distance on the right. So yeah, I wanted to show you that, and it's kind of cool. Let's continue. Okay, so that's what gravity is. It is acceleration, and a mass is going to accelerate faster and faster as it falls. If we've got a mass up high, it has more gravitational potential energy. So let's calculate the gravitational potential energy of that those masses, well, that mass on my ladder in my yard. So yeah, let's take a look at that. I'm going to flip the slide here. Let's look at those 2 pictures again. Okay, so we've got the picture on the left here, and yeah, we're going to use the formula for gravitational potential energy. As you write this out with me, say gravitational potential energy in joules, right? Energy is always measured in joules, is going to equal the mass, okay, so it's about 0.5 kilograms, times gravity on Earth, so that never changes, times the change in height. And so our mass here is going to be, I'll just put it here, is going to be 0.5 kg, and in this case our change in height is 0.75 meters. On this side here, we've got a mass. Mass is the same. It's the same weight. It's the same mass, 0.5 kilograms. Change in height though this time, and I'm saying this is 2.25 meters of change in height. And here's your toe, and again, you know, imagine this is definitely, let's select it like that. This is definitely going to hurt. This would injure you, right? So that definitely has more joules, more gravitational potential energy. We're not going to let it fall on your toe, don't worry. Let's calculate, excuse me, each of these using this formula. So we know our mass. Here's our given information, 0.5 kg. And write it out like this. Write your formula, write your knowns. G, acceleration due to gravity on Earth, 9.81 meters per second squared. And change in height, in this case, it's 0.75 meters. Plug it in, solve. 0.5 kilograms. Write it out first, though. Don't just type it into your calculator. Write it on paper so you can see it, so you can also make sure you're doing the units and everything correctly. Meters per second. It also allows you to check if you've got it written down properly. And then change in height, 0.75 meters. I'll plug that into my calculator here, and let's see what I get. Should get 3, now we don't need this many decimal places, 3.67, 87, yeah, I mean, you don't need that many. Now, looks like we only have one. Let's just add a 0 here just to make it a little easier for us. That is what I wanted to do. Seriously, that's what I wanted to do. So we got 2 significant digits. That's the fewest number of significant digits, so down to 2. So it's going to be 3.6. We either round it up to 3.7 or we round it down to 3.6. 2 sig digs, just C2 here. And yeah, you either round up or down. In this case, we're going to round up, so it's going to be 3.7 joules. Okay, cool. Put a little box around that. That's our gravitational potential energy, EG. Let's see how much gravitational potential energy is in this next one. Again, write the formula out, times G, mass, times gravity, times change in height. Our mass is the same, 0.50. We'll add a O there, just to show how exact our mass is. Gravity, you know what gravity is. It's good to do this a couple times right now, so write it out again. 9.81 meters per second squared. Change in height this time was 2.25 meters. Plug it in. Go ahead, hit pause. Again, just 2 significant digits for your answer. I'll catch up to you now. 0.5, so my mass times my gravity, meters per second squared, and my change in height, 2.25 meters. Plug that all in, so 0.5 times 9.81 times 2.25. Looks like we get 11.0362. Again, we don't need that many significant digits, we just need 2. So we go here to 11, and I mean, we either round it, it would be either we'd either, sorry, we'd either round it up to 12 or stay at 11. We're just going to go to 11. Yes, I can speak. 11 joules, energy of gravity. There we go. Okay, we've done a couple example questions. Again, this makes sense. We know that in that picture up there, that indeed this mass that's higher up in the ladder, same mass, is going to have a lot more gravitational potential energy, and the formula proves it. And yeah, I don't want to find out what 11 joules feels like on my foot. So let's do some more. Let's do another practice question here. Gravitational potential energy, right here. Now hit pause. And of course, we're solving, so make sure, given, required, analysis, solve, and then do your paraphrase. So hit pause and try this on your own, and then press play. Okay, let's take a look at this. So given, required. I like to always look at what's required so I know what the question's asking. Analysis, what formula am I going to use? I think we know, but it's still a good practice to ask your brain, is that the right formula? And then we're going to paraphrase after that. Just write a little sentence. But let's come back here. We are looking for gravitational potential energy. So underline that, write it out. I'm going to find Gravitational. And think about what that is and look for it on your formula sheet. What are some of the factors of that? Okay, we know it's EG, or energy of gravity, mass times gravity times change in height. Now let's see, and we've already done the analysis, I guess, and we've got the formula there, and that's great, but let's see what we're given. Which information are we given here? Do we have the mass? Yeah, 1.2 kg right there in the question. We've always got gravitational potential energy, right? You know your number for that. What's my change in height? That's in the question too. That's 1.8 meters. This, of course, 9.81 meters per second squared, that acceleration due to gravity. And EG, maybe the question gives it to me? No, don't know how many joules. That's what we're going to solve for. Let's plug it in. Again, that is indeed our formula. Mass times gravity times change in height. Do the solve. 1.2 kg times 9.81 meters per second squared times the change in height. So we've lifted the book off the floor, 1.8 meters. Oh, that was a lot of work. Looks like our answer is going to be 2 significant digits. Plug it into the calculator. Make sure you're getting 21.18. Now again, we don't need this many decimal places, but let's just write it out a bit here. Joules. Okay, we only need 2 sig digs. Again, I know that. What's the fewest number of significant digits in the question? And it's 2. So it's either going to be rounded down to 21 or rounded up to 22, but it's 21. 21 joules of gravitational. So we do our paraphrase. Energy in the book. Put a little box around it. That way you know where your answer is. You can double check it. Do double check these. Make sure to check mine. Make sure I got it right. Send me an email definitely if I got that wrong somehow, and that can definitely happen. So yeah, check that. Let's try another. So we solved for gravitational potential energy, but remember, maybe a question is going to give us gravitational potential energy. So how many joules? And maybe it'll ask us to solve for mass, because it would also give us the height. But maybe a question would give us the gravitational potential energy, give us the mass, but not give us the change in height. And we'd have to rearrange the formula. I'll show you how to do that, and you'll want to write that on your formula sheet anyway. So yeah, let's take a look at this next question. What does it ask? Read it carefully. Press play. Press pause and try to solve it on your own. But yeah, you can watch me do this here. So what is our given information? What's required? Do some analysis. In other words, what's the formula we're going to need? And then solve it. And then, of course, after solving, we do our paraphrase. But I always like to go with required. How high is the stairs? Oh, boy. Height of stairs. Now, I'm not sure what formula off the bat, and that's okay. I say to myself, okay, so probably going to need a height in meters, I guess. So let's go to given then. Okay, we've got energy. We lifted a book up. That's gravitational potential energy. Okay, I think we're giving a hint what formula to use. We've got a mass, 12 kilograms. We've definitely lifted something up, right? So that is against gravity, 9.81 meters per second squared. And yeah, change in height. Oh, that's what I'm looking for. Unknown meters. So in terms of analysis, yeah, I'm going to write out the formula for gravitational potential energy, but I'm going to need to rearrange it, right? But let's write out what we know. Let's stick with what we know and always start with what you know with this stuff. Okay, I need the mass times gravity times my change in height, but I've got to solve for change in height. Now to do that, we would just divide mass times gravity out of this side because it's been multiplied in and then divided on that side. Now you can just write this as how to solve for height. Change in height equals gravitational potential energy divided by mass times gravity. And we have that information, right? Like if you take a look carefully, we are given how many joules. We're given the gravitational potential energy. We're given the mass. And of course, we've got gravity. So we can indeed solve for height. So just make sure, take a look at this and make sure this is making sense. And of course, to solve for height, that would be the formula. So let's plug it in, solve for height. EG, or how much energy was put in to this box, 565 joules, divided by my mass, 12 kilogram box, times gravity. Had to lift it up against gravity, 9.81 meters per second squared. Now it's a set of stairs. We don't worry about kind of the diagonal distance. It's as if we've lifted it straight up, you know, and so yeah, let's kind of figure that out. Now, when we're doing this, we got to respect order of operations, solve for the bottom, get a number on the bottom. Don't round it, right? Like have the full number. So on the top, we've got a number, 565 joules. But take out a calculator, go 12 times 9.81. Get a full number there. I'll write it out, but make sure that I've got it right. So 117.72, okay? And as many decimal places are there, write them out. Do not round at this point, right? Now we plug it in. 565 divided by 117.72, and you will indeed get 4.8. And it's change in height, meters. 4.8 meters up the stairs. There's our paraphrase. Okay, cool. Okay, let's try another one. I'm going to flip the slide here. Last one will do for now. Read it carefully. What information is given? What information is required? Do some analysis and solve it. Your notes, your answer should look exactly like this. So the word given, the word required. Be consistent when you're solving math and science problems. This also structures your thinking and gets your brain to relax, because that's really critical. Because you're writing out things that you know. You know that there's going to be some given information. You know the question is going to ask a question. Oh, looking for gravitational potential energy, looking for EG, and we know the formula by now. Mass times gravity times change in height. Well, what are we given here? Are we given a mass? Absolutely, right there, 3.8 kilograms. We've got gravity, you know that already. Change in height, let's see if that information is on the question. Yep, 2.1 meters, and of course this is 9.81 meters per second squared. Analysis is solved, let's just plug it right in here. 3.8 kilograms, and that is indeed the mass. The picture had to be lifted up against gravity, 9.81 meters per second squared of acceleration pulling. That's the pull due to gravity, you can feel that. And your change in height, 2.1 meters. Good distance, by the way, so picture's up good. Plug that in a calculator. We get 78.283. We do not need that many. Looks like it's just going to be two significant digits. So 1, 2, 78. So either we stay at 78 or go up to 79. Stay at 78, right? Because it's only 0.2. 78 joules of energy to lift. You can write out a big full sentence here. To lift 3.8 kg, 2.1 meters straight up. Straight up is against gravity. Boom. Okay. Make sure to do the practice questions for gravitational potential energy, and then, yeah, time to do the assignment once you've completed those. Okay, take care.